All right, let's take a look at an example of horizontal circular motion. In this case, it'll be static friction that's causing circular motion. Let's say we have a 5.18 gram ladybug, and it's at rest on a rotating record that has a diameter of 25.4 centimeters. The record begins to spin at a constant speed, and the ladybug makes it one full revolution around the record in 4 seconds. Let's say we wanted to calculate the tangential velocity of the ladybug, or the tangential speed of the ladybug, as it is traveling in a circle along the record. Let's recall that the tangential velocity of an object can be found by taking the circumference of the circle that it travels around and dividing that by t, the time it takes to make one full revolution. And in this case, we were both given the diameter and the time. So I know that the diameter, which is equal to 2 times the radius, is equal to 25.4 centimeters, which I'll convert to meters immediately. That is 0.254 meters, right? Divided by 100, move that decimal place over 2 to the left. So if that's my diameter, my radius must be 1/2 of that. So my radius will be 1/2 of 0.254, which will be 0.127 meters. Okay. Now, I also, in this case, was given the time period, big T. And big T is 4 seconds because it takes 4 seconds to make one full revolution. If you were told how long it took to make 2 revolutions, you would just have to cut this time in half, right? It's the time to make 1 revolution. So this will be equal to 2 pi times 0.127 meters divided by 4 seconds. And I'll go ahead and drop my units here. Plugging this into my calculator, I will get a tangential velocity of about 0.20 meters per second. And just a quick units check here. Radius was in meters and time period was in seconds. So there we go. My units should be meters per second. All right, we're good. I'll go ahead and label this on my diagram as well. The tangential velocity of the ladybug will be pointing in this direction if the ladybug is on the circle right there, and that is equal to 0.20 meters per second. I'd also like to point out that I know the radius of the record was given, and the ladybug's not quite on the edge of the record, but for the sake of example, let's just say that the radius is given to where the ladybug actually is. In other words, if I were to label my diagram, let's say that this distance between the ladybug and the center of the record is that 25.4, that would be the diameter. That would be 12.7 centimeters, just for the sake of example. So if we wanted to calculate the centripetal acceleration of the ladybug, a sub c, or in this case, we can also say a sub n is how I like to call it, that would be equal to the tangential velocity squared divided by the radius. In this case, we've already calculated the tangential velocity. It's 0.20. We go ahead and square that and divide by the radius, which is 0.127, and that will give us an acceleration of 0.31 meters per second squared. And just a quick units check here, right? Meters per second squared over a meter, that would be equal to meters squared over seconds squared over a meter, and then that meter on the denominator here will cancel with the numerator there, the exponent, and we'll get meters per second squared, and that checks out. Good. All right. I'll go ahead and label this on my diagram as well. I'll do this in a different color. We'll do this in blue. The centripetal acceleration of the ladybug will point directly into the center of the circle, like so. That will be the direction of acceleration of the ladybug. If I wanted to then finally calculate the net inward force exerted on the ladybug, that would be, in other words, the sum of forces pointing in the direction of the circle, or the net inward force. That would be equal to the mass of the ladybug multiplied by the acceleration of the ladybug pointing into the circle. In this case, I was given that the mass of the ladybug was 5.18 grams, which I will go ahead and write as not grams, but we want to divide by 1,000 to get to kilograms. So that would be 0.00518 kilograms. I'll go ahead and plug that into my net force equation. That would be 0.00518 multiplied by this 0.31 for my acceleration. That would give me a net inward force of, this would be 0.002 newtons. Not a lot of newtons, but it's also not a very heavy ladybug, and so that's we should expect that. The mass in here, in this example, was in kilograms, and the acceleration was in meters per second squared, so I just want to make sure that is what we call, right? This is equal to a Newton. So we're good. That works out. So the answer here is 0.002 newtons. I've rounded here just to one significant figure. And I'd like to be clear, this net inward force, this is just another way of saying what is the centripetal force exerted on the ladybug, right? That is the net inward force. All right, now let's say that we wanted to calculate the static frictional force between the ladybug and the record. How would we go about doing that? Well, it's actually a bit of a silly question in this case because we already did. What is the force responsible for keeping the ladybug moving in a circle? Well, we talked about this earlier. The force of static friction between the ladybug and the record is keeping the ladybug moving into the center of the circle. So I can say the force of static friction, right, acts into the center of the circle. I know that it has to because the acceleration of this ladybug points inward, and the net force takes the direction of the acceleration. In this case, I only have one force pointing into the circle, right? So my sum of forces in the direction of the circle, right, is just the force of friction. We can say Fs for short, right? I don't have any other forces pointing in the direction of the circle's radius. Now, to be clear, if I draw a free body diagram for the ladybug, right, we'll go ahead and do this. We're going to need this down here, so I'll do it down here. A side view of the ladybug would look like this, right? The normal force would point upwards. The gravitational force would still point downwards. And let's say that the ladybug's somewhere on the right side of the record. So let's say the ladybug's right here, right? Then the frictional force would point to the left. And so I could show that on my diagram like so. It's going to point directly into the center of the circle. So the only force pointing in that direction is this static frictional force. Yes, the normal force and gravitational force are still acting on the ladybug, but that's happening in a different direction. I could apply a different force balance to get the sum of forces in the y direction, but I'm not interested in that direction right now. So if we've already calculated the net inward force, we have actually calculated the force of static friction as well. It's that same 0.002 newtons that we got earlier. But that's just the force of static friction between the ladybug and the record right now at this velocity, right? So what if we wanted to calculate the maximum velocity? What if we wanted to see how fast can we spin this record without the ladybug sliding off, right? If the coefficient of static friction between the ladybug and the record is 0.4. Now, I'd like to pause and just point out an important idea right now that you may be thinking. If we were to spin this record very, very fast, the ladybug would begin to slide off the record, almost as if some force were pushing it outside to the outside of the circle. It's important to note here that this is not a real force. This is something we sometimes have called the centrifugal force, right? I'll write this out. And I'd like to point out again, this is not a real force. There's nothing actually causing this force. What this actually is the inertial tendency of the ladybug to want to keep moving in the direction it was moving, right? The ladybug wants to keep going in a straight path, but the force of friction keeps the ladybug moving in a circle. And so its inertia is essentially pushing it out of this circle, if you will. So this is not a real force. I just want to be clear about this. We call this a fictitious or a fake force, but it's a force that we have to basically think about to make this situation work. The ladybug actually feels like it's being pushed out of the circle. And so for the ladybug to explain what's happening to it, the ladybug can say, well, there's some fake centrifugal force pushing me outside, right? That's what the ladybug has to say to make sense of what's happening to it. But we know that that's not actually the case, right? The ladybug's inertia is the reason it's going to be pushed out of the circle. But we think about this idea all the time, right? We think when we see an object traveling in a circular path, that there is some force pushing it out to the outside edge of the circle. And so I want to point this out right now because this is something that very commonly students will think of or even talk about the centrifugal force as a real force. And it's not. It's a phenomena that we know exists because of inertia, but there's nothing actually creating a force in that direction. It's simply an inertial tendency of that object to want to continue traveling in a straight path. And so if that helps also justify why the force of static friction points into the circle, I know that can be also kind of a weird idea. That helps me think about why static friction points into the center of the circle. It's resisting this fake centrifugal force or this inertial tendency of the ladybug to want to move to the outside edge of the circle. So to answer part E here, I'll show you two different ways of thinking about this. The first, ignoring the centrifugal, this fake force, is to think of the centripetal force or the net force pointing into the circle as the requirement, right? This is what is required to keep circular motion. In other words, whatever force is causing circular motion needs to be at least this much. And if it's not, the object's not going to move in a circle. It's just going to slide off or continue to move in a straight path. So what we can say is, right, the force of static friction, and we'll say the maximum force, right, the largest friction could ever be, has to be, right, greater than or equal to this centripetal force, or the sum of forces pointing into the circle, right? If the frictional force is less than the force pointing into the circle, right, the requirement, this object, the ladybug, will not move in a circle. And so we can say that the force of static friction must be at least or greater than this requirement to keep circular motion. And if I were to expand this, that would mean that the coefficient of static friction times the normal force on the ladybug, right, which must be greater than or equal to the centripetal force or net inward force, which is equal to the mass of the ladybug multiplied by the centripetal acceleration of the ladybug. And I can expand this centripetal acceleration term as well to say that, again, I'll write this out again on the left-hand side, must be greater than or equal to the mass times the tangential velocity squared over the radius, right? And I know in this case that Fn here, the normal force of the ladybug, is balanced by the gravitational force of the ladybug, and if this is equal to mg, then Fn must also be equal to mg in this scenario. So I can say that the coefficient of friction times mg must be greater than or equal to the mass of the ladybug times the tangential velocity squared over the radius. I have an m on both sides, so that I'll actually go ahead and cancel out. And that would mean that the velocity, the tangential velocity, right, I'm going to go ahead and flip it to the other side, must be less than or equal to here, right? I'm going to multiply by r on both sides, and then take the square root. So that would be the square root of r times mu sub s times g. Right. And so what I see here is that any velocity less than or equal to, right, this expression will keep the ladybug on the record. And so the maximum velocity would be when, obviously, they're equal to each other, right? When the velocity is that square root of the radius times the coefficient of friction times g. And so I won't do the calculation here, but you can please finish this calculation in your notes to calculate this velocity. Now, the second way of thinking about this, if you're like, I don't really like that very much, the second way of thinking about this is, when would the force of friction at its maximum be equal to that fake centrifugal force? This is, again, a fake force. It's not real. So the centrifugal force would have the same equation as the centripetal force. So this would still be equal to m times the acceleration pointing inward, or again, this AC term, which is equal to m times vt squared over r. They have the same expression, right? It's the same idea. Again, this one just doesn't exist. And I know that at the point the ladybug, like right before it slides off, right, the most that the centrifugal force, this fake force, could be is the maximum force of static friction. If it were to be any more than that, then the ladybug would start to move in that direction of this, again, fictitious inertial force. And so that would give me the same expression, right? The force of static friction maximum would be equal to this vt squared over r times m term. And again, this would be the same thing, right? The normal force times the coefficient of friction would be equal to vt squared over r times m, and then you could solve for vt just as we did before. So the answer is no different. The way we think about it is just a bit different. If you like thinking of this fictitious centrifugal force, you can always, show this. Don't show this on a free body diagram ever. It's not a real force. But you can, do this when you're showing a sketch or a diagram to help you make sense of what's happening. Because we already have this internalized idea as humans of what's going on here. Even if it's not totally correct, it can be a helpful tool for thinking about how to analyze situations like this.